Okay, so in this video, we're gonna talk about the mass spectrum. Be familiar with the mass spectrum. Just like an IR, you have to look at it often enough so you know what to look at. Okay. All right. So the first thing you look at when you have a mass spectrum, the most important thing is this peak. Okay. We call it M plus peak, so it stands for molecular ion peak. This peak represents the mass of the intact molecule. What does intact molecule mean? Well, think about this. In the mass spectrum environment, what happens? So ionization and then fragmentation, make them an ion first, and then they start falling apart. Okay, the intact molecule is still the whole molecule, hasn't gone through the fragmentation yet. This is the heaviest molecule and represent the actual compounds that you add into the instrument. All right, but of course, this species, what does it look like though? Of course, it won't look like this because this guy have no charge, and neutral compound, neutral species does not cannot be detected. Okay, because they have to go through the magnet, right? So the what does this compound, this species look like? So it looks like this. When it get the compound, the sample get ionized, it become a radical cation. That's what does it look like? Okay, so we call this the molecular ion peak. Okay, so it's a peak of the intact molecule. Now, that's what we focus on the most. The rest, anything that's smaller or lighter, we call fragment peaks. Okay, so of course smaller. So from this guy falling apart, become fragments. All right. Some of you may ask, hey, hold on, what the heck is this peak? How could we have anything heavier than what we add? We add this 16. How do we get heavier? Well, give me a few videos. I'll explain this peak to you. Okay. All right, now from this mass spectrum, so after you look at the molecular ion peak, so what else we got? On the y-axis, we have relative abundance, which is the relative amount or relative number of each species based off, or it's relative, right? Gonna be based on something. It's based off the tallest peak, which is we call best peak. Okay, the best peak is set as 100%. Anything else is based off the 100%. For example, the mass per chart of 16 is 100%. The 15 only 85% of it, compared to 100%. 14 9.2, 13 12, and 3.91. The relative height depends on the stability. If a species is stable, you obtain at the detector the highest amount. If it's unstable, you don't get a lot of it. Okay, and by the way, so the molecular ion peak is not always a best peak. Again, it depends on the stability. If the molecular ion peak is not that stable compared to the fragment can be the taller peak. It depends. Okay, so that's the y-axis. Now the x-axis, we have mass per charge. In this class, we're going to focus on the species that have charge only one. Any number that you see right here, for example, 16 is 16 per 1. So that's a 16 basically. All right, from this, so this is a mass spectrum. What information can we obtain from a mass spectrum? Here we go. You can obtain molecular ion peak. Of course, that's the first thing you look at. Is tell you the molecular weight of the compound, of the sample. Okay, we can use this. We can use nitrogen rule on it. We'll talk about how to use it and what it's for. Rule 13. This one will get you to the molecular formula, which is really important. Okay, you can do a degree of unsaturation on it. And plus 2, I tell you about bromine, chlorine. Okay, fragmentation patterns. This one we don't learn it in this class. That's for graduate students. Okay. All right. So we're gonna take a look at the first information, which is molecular weight. Next video.